Okay, moving along now to ASME. Okay, so we have this thing we call the ASME Boiler Pressure Vessel Code, or BPVC for short. And it has a whole bunch of sections. And, there's a nuclear section, there's this section, there's that section, there's all kinds of stuff in that boiler pressure vessel code. So the main ones we're concerned with are section 1, which is power boilers. Power boilers. And then I think another biggie for us would be section 8, VIII. They use Roman numerals, okay? So if you don't know your Roman numerals, time to learn them. So section 8 has two divisions. There's division 1 and there's division 2. For us, I think that division 1 is probably more important. So most of the pressure vessels that you see in your plants are going to be div 1 vessels, but there certainly are div 2 vessels out there. And then we've also got section 4, which is fairly important, but less so at the third class level, and probably more so when you say go into inspections and things like that. You'll certainly be inspecting these things, and those are heating boilers, and you learned about those last year. So a section 4 boiler is a heating boiler, and a section 1 boiler is a power boiler. And so what exactly is a power boiler? A power boiler is a boiler that's got a maximum allowable working pressure. Okay, I'm just going to call it mop, okay? So if you hear me say mop, I'm not talking about mopping the floor. What I'm talking about is maximum allowable working pressure. And so it's got a mop of over 100 kPa gauge. That's for a steam boiler, because we also find that we do have power boilers that are in hot water service. And so if it's a hot water boiler, it's a mop greater than 1100 kPa gauge. Or a boiler operating at over 120 degrees Celsius. Again, that's for water. So we certainly have hot water boilers that must be designed by code to be power boilers. And where that exists, they often say, well, the Power Engineers Act or the Power Engineers Regulations, whatever, it kicks in. So you can have a first-class hot water plant. And I'll give you two examples. In Manitoba, there was the nuclear research facility in Pinawa, Manitoba, was a first-class plant. They didn't make steam. They had high pressure, high temperature, hot water. And there was another place that I inspected, was the North End Water Sewage Treatment Plant in Winnipeg, which was a first-class plant because of its high pressure, high temperature, hot water. And all their boilers were power boilers. Now, there's another code, it's called the pressure piping code, and it is not the same as the boiler and pressure vessel code. This one here has got a whole bunch of sections, including refrigeration piping, it's got building services piping, it's got all kinds of different pipings, and the one that concerns us the most is the B31.1 power piping code. And power piping is the piping that's associated with power boilers. So if we want to find out something about blow-off piping requirements, if you want to find out about feed water piping requirements, that is not in ASME code section 1. This is all in B31.1 power piping code. And I do believe that you can get this one from the Reg Earhart library as well. Now, one of the things that all of these codes have in common is that they are all construction codes. And they apply to new construction. They don't apply to used boilers, if you will, okay? They're construction codes. And basically what it's saying is, if you want to build a boiler, this is how you do it. However, there's another thing. They're also not handbooks. They are not design handbooks. Some people think, oh, all you got to do is open the book and connect the dots. No. There's a lot of, well, I mean, it's really up to the engineer how they want to design the boilers. This is not like a plug and play, right? This is full creativity, full-on creativity here. All right, so let's do something a little bit different now. And choo-choo just went off the track, but it'll come back. Okay, here it is. Let's take a look at certain parts of boilers that we call cylindrical components. So you tell me what parts of a boiler are cylindrical, and I'll start writing them down.
It's probably easier to name the things that aren't cylindrical.
Tubes.
Okay, well, what kind of tubes? Got to be specific.
Or water tubes.
Right. Any other tubes?
Or fire tubes.
Okay. Any other kind of tubes? Furnace tubes.
Furnace tubes, yeah.
Okay, what else is cylindrical?
The drums.
Yeah.
Drums. Steam drum, a drum, shell. Drums and shells. Okay, headers, pipes. Now, four of these items have a lot in common, and two of them are different. Okay, this is like Sesame Street. Two of these things are not like the other. Two of these things just doesn't belong. What are the two things on that list that are different from the others?
Drum shell.
They're different. How are they different?
Because they are bigger and they need like
Drums and shells. Okay, so bigger might be a criterion, but you can get mighty big furnace tubes. Okay. Anybody want to attempt?
Would it be the water tubes?
The water tubes to which?
Because they're bent?
Bent. Like we don't bend drums and shells. Pipes could be bent.
Yeah, I tried to log into.
Well, now that I got you thinking.
Is it the water tubes and the fire tubes because they're exposed directly to heat?
Oh, okay. Well, now that I got you thinking, I'm going to answer it for you.
Okay, I'm looking at the drum and shell
Yeah,
because they
because
have another, like they could have
I
tubes
think
in them.
at the front, you call it, forgot the name.
Okay, thank you for playing along nicely, because there are probably a lot of things that we can say about, all of these components, but the major distinction is fire tubes and furnace tubes are like this here. They have got external pressure. They're trying to collapse or buckle the piece. Whereas everything else, the water tube, the drum, the shell, the header, and the pipe, they all have internal pressure. Different forces, different stresses. And so then that's how we're going to categorize them, because that's how ASME code categorizes the cylindrical components. There are cylindrical components under internal pressure, and there are cylindrical components under external pressure. You will do design calculations for cylindrical components under external pressure. I think maybe we might, if I recall, we might do corrugated furnaces, but that's about it. Once you get into second class, you'll do those calculations. Um, they're not that much harder. They're just kind of more involved and sort of a pain in the butt, and it's not really something that you need to know at the third class level. But for water tubes, drums, shells, headers, and pipes, these are all components that resist internal pressure, and so then that's really the thrust of ASME code design calculations for the third class. So, next question I have for you is, what determines MOP? You've got these boilers, they got a maximum allowable working pressure of, I don't know, 4 megapascals. What determines that? How did the manufacturer come up with that idea?
Isn't it like the maximum pressure and then times like the safety factor gives us our MOP?
Okay, so you're going into some really meaty stuff there. Okay, so let me address this, because this could take us to the wrong place. So let's get into the meat right now. What you're talking about is, I take a material and I do the stress strain analysis and I determine the yield point. Okay, and then I say, well, you know what, I don't want to operate my boiler near the yield point. What I want to do is have it down here somewhere. Okay, so let's say here, that's my MOP. Actually, that's the maximum allowable working stress. And so let's say that amount of stress that we permit. So if we take the yield strength, divide that by the maximum allowable working stress, we get a factor of safety. And that's what you're talking about, right? What you're saying is, we want to operate the boiler with material stress that is well below the yield point by some safety factor. Because even if we get a little overpressurization occurrence, hopefully our boiler isn't going to bulge, it's not going to fail, it's not going to, right? So we've got a maximum level working stress. But I just kind of gave away something, because we went really deep into the meat there, the letter stress, the S for stress. Okay, let's go back to our max working pressure business here. What are the factors in determining the maximum level working pressure of a boiler? Well, here's the first one. It's the maximum allowable stress of the material. We know from a load extension diagram, we can determine the ultimate strength or the ultimate stress, and we can determine the yield point and all that kind of stuff. But we should also know that stress varies with temperature, or the allowable stress of the material varies with temperature. So what we find is at very high temperature, a material is weak. And at, say room temperature, it would be much stronger. So we need to know the temperature of the material, and we know the temperature of the material when it's operating, okay? So if we've got a superheater that's operating at 500 degrees Celsius, we need to know that it's at 500 Celsius, right? And we design it for that temperature. But every material is different about how it behaves at temperature. So we need to know the allowable stress at temperature. And that allowable stress at temperature will build in the factor of safety. So notice that on my little diagram here, I did maximum allowable working stress. We get this information from ASME 2D. ASME Boiler Pressure Vessel Code Part 2D. And that's a table of all of the materials that are permissible for boiler and pressure vessel construction, and how their allowable stress varies with temperature, and the factor of safety is actually built in to all those published stresses. Okay, what else? Another factor in determining the maximum allowable working pressure of a boiler. And I gave you an example in the previous content that we covered, not the stuff today, but the corrosion stuff. Remember
Material of construction.
Material of construction. Okay, that wasn't the one that I was going for, but that's definitely one of those. Okay, construction material. And the material of construction, basically ASME 2D has a whole bunch of materials, like thousands upon thousands of materials. And for each one of those materials, they have unique behavior at temperature. So what we're going to have to do is look up in ASME 2D, we're going to have to find the material of construction, and then we're going to have to determine the temperature at which the boiler operates at and find out the allowable stress at that particular temperature. So yes, material of construction, absolutely. Okay, I was talking about ultrasonic testing. And we use ultrasound for testing for volumetric testing, and we also use it for what? There you go, thickness. Obviously, a thicker material can withstand a greater force, so the maximum allowable working pressure is going to be dependent on the thickness of the material as well. Okay, now here's one that might not immediately connect with you, but the diameter of the component, the pipe, the water tube, or whatever diameter, okay? So let's now take a look at how these items come into play in actual boiler and pressure vessel design calculations. So let me just clear this stuff away. clear those little fragments away too. Okay, so what I'm going to do here is make a boiler shell. Or actually, this is going to be a cylindrical component under internal pressure, not a boiler shell. It could be a shell, could be a drum, something like that. And so inside there's a particular pressure, and that pressure is exerted out in all directions on the internal surface area of that vessel. And this vessel has an outside diameter of d, and the material has a particular thickness, small letter t. And so knowing the pressure and knowing the area on which that pressure acts, we can come up with a force. So if I take a look at a shell, I can see that there are forces that are acting circumferentially, and there are forces that act longitudinally. Okay, and so this gives us two stresses. First of all is the circumferential stress, and I'm going to make sure that that one is drawn in the correct color. Okay, this is here. That's our circumferential stress. And then the longitudinal stress. That's this one here. So let's first take a look at the circumferential stress. Okay. So I am going to cut this shell in half this way. Okay, and I'm going to get rid of the top part of it. So all that I'm going to be left with is this part. Okay. So the pressure that's acting inside of that shell is acting on a particular area, and I'm going to mark that area with, oh, what color? I'll use color. It's easy to see. I'll use greenish. Okay, so I've got an area here in the middle. That area is equal to the outside diameter of the shell minus 2t, because I've got a thickness here and I got a thickness there, times the length. Okay, makes sense? Or does it?
It does.
It does? You sure it makes sense? Let me just clarify this a little bit. Now I've got an end view. Okay, there's my end view. And I got pressure inside of there. And some of that pressure has only X components. Some of the pressure has only a Y component. And as I follow the curvature of the shell, I end up with a particular y component that diminishes and an x component that actually increases. Okay? The net effect of that is the pressure exerted only on this area here. If I take the sum of all of those components and I resolve them all to be in the y direction, what I end up with is this flat surface area. So if you imagine it this way, I take that shell and I'm going to look at it on end, and I see a strip of material there, and I see a strip of material there. This then is the area that the pressure acts upon. And that area is d minus 2t minus, a thickness here and a thickness there, d minus 2t times the length. Okay? So we call that the projected area of the shell. Okay. Projected area. Okay, so we know that then the force is equal to the pressure times the area. In this case, it is the projected area. And so we've got a particular force, and then that force is resisted because you know about stress and strain, and you know that stress is force over area. So what we have is, what is the area when we talk about stress? We're talking about the area, the cross-sectional area of the material that is resisting stress. So I just highlighted that material as this sort of reddish color, right? So there's a particular area there. So the cross-sectional area of the material resisting stress is equal to the diameter of the vessel no, sorry, I just had a little brain fart there, folks. Sorry about that. It's just simply 2 times T times L. We've got two thicknesses, one over here, one over there, times the length of the vessel. So, oh, I didn't go where I wanted it to. There, that's where I want you to go. Get away from there. There, 2TL. So we know that stress is equal to force over area. And the force in this case is the pressure times the area. Pressure times the area. So stress is equal to the pressure times the area. So the pressure inside the vessel times the area, which we said is D minus 2T times L, over the area that's resisting the stress. That's this one here, 2TL. And if you're watching, you'll see then that the length cancels out. So the length of the vessel really doesn't have any factor whatsoever on the maximum allowable working pressure of a boiler. So now let's just clean this up a little bit, okay? And we'll put it this way. Stress in this shell is going to be equal to P d minus 2t over 2t. Now recall we just went over some of these things. What is the stress? The stress is the maximum allowable working stress. The P is the maximum allowable working pressure. T is the minimum thickness. D is the diameter of the shell. So we're not going to be solving for stress. We can do that. We can do this as a stress analysis, but what we're trying to do is figure out what's the maximum allowable working pressure, for example. So if I solve this for maximum allowable working pressure, I get 2ST over D minus 2T. Okay. Now, we are getting close to the end of our class today, so here's what I want you to do. I want you to go to ASME code, and it is posted, and I want you to go to PG 27.2, that's the code reference, and PG 27.1, or yeah, PG 27.1. Okay, I want you to go to both of those code places, and what you're going to see is a formula that looks very similar to that. And what I want you to do then is figure out how is it different? And and how is it the same? And then the next thing that I want you to do is I want you to transpose that, solve for minimum thickness. So that's our introduction to the ASME code. This is the basic statics, I guess, if you will, the basic mechanics behind determining the maximum allowable working pressure or determining minimum thicknesses, given that you already have a maximum allowable working pressure in mind. And everything that ASME does basically builds upon this. So the whole idea with this is to kind of get rid of the mystery from the get rid of the mystery from the codes. Okay, any questions before we leave? I see there's a comment that my audio was cutting out. I hope that I hope it did improve as we went along. Any questions or comments? Okay, then we will see you tomorrow at 11 a.m. Have a great day, everybody. Enjoy the weather. It's going to be a beautiful day.